Hi, my name is Jim. Switch mode regulators are in favor today, replacing linear regulators, and the principal reason is that they're a lot more efficient. So let's kind of talk about the difference between the two of them. So the advantage of a switch mode regulator, and we'll see why this takes place a little bit later, has to do with the efficiency, neta, which is expressed as the power out divided by the power in, and if you wanted that in a percent, that would be times 100%. And this is especially true if you're operating a device from a battery or cell. And cell is a single battery, if you will, a component of a battery, where you want to maximize the lifetime of the battery. What you don't need to be doing is wasting energy in the form of heat with a linear regulator. So you want that regulator to be as efficient as possible in the process of converting one voltage to a different voltage. The disadvantages are that they're noisier. They have an inductor and a switch, and the inductor, I guess you could look upon as being a small antenna. There's circuit noise associated with them, and the cost, well, in quantities it's probably very similar. Now let's take a little look at the noise on a circuit trace, because this is very important if you ever get into working with or laying out circuit boards that have switch mode components. There's a very right and a very wrong way to do this. Now I've taken the absolute worst case example here, where I have my power supply coming in, say, I don't know, bridge rectifier. This in itself may be a switch mode power supply. And I have my ground line running on over, wiggling around a bit, and feeding the ground to the switching regulator. And what the switching regulator does is that it produces pulses of current as it switches. Now, sitting in the middle of this ground, we have another device, an analog or digital device. It doesn't matter. You can analog, of course, is susceptible to noise, and digital noise just simply changes the threshold voltage, where ones become zeros and zeros becomes one, as in not good. So if we take a look at a printed circuit trace in a distributed form, is what we see is that it's a series of inductors and resistors. It's not a good conductor at all. You need a very heavy trace, like a heavy copper bore, 4 ounces. That beat per square foot would be an example of a very heavy board, typically 1 ounce. But anyway, thicker the copper the better, because it reduces the effective series resistance and the inductance of the trace. So as these pulses flow through the ground, what we get is plus and minus drops across this, and since this device is connected in the middle, its ground is going to bounce. And as I said before, in a digital circuit, what this tends to do is change the logic threshold, and in an analog circuit it can simply pollute the output, be that audio or video or whatever. So a good design here would basically have this part, this part's ground connected directly to your main filter capacitor, and then this part's ground connected also to the same point, so it doesn't share any of the ground with the switcher. And that's true for anything that's noisy. You want to go back to a central ground point, and that's called starring out from the grounds. Once you build a bad board, you don't fix it. You have to replace it. So let's take a look at the efficiency, and in this example we have a linear regulator. Its output voltage is 3.3 volts, and this would be related in a switch mode concept to a buck mode regulator. And all that means is that the output voltage is going to be lower than the input voltage. Well, in this example here, I've got a 3.3 ohm load, and it's a 3.3 volt regulator, and I have 1 ampere current flowing through the load resistance. Now there's a little bit of quiescent current here, but I'm going to throw it out. It really doesn't contribute much. And if I have 1 ampere flowing out, I also have to have 1 ampere flowing in. It's KCL. And suppose that I'm kicking this off from a 10 volt power supply. What that means is the voltage drop across the regulator is 6.7 volts. Now the load power in this case is going to be I squared R. 1 squared is 1 times 3.3 ohms, which is 3.3 watts. And the voltage loss across the regulator being 6.7 volts with 1 ampere flowing through the regulator means that the regulator's power dissipation is going to be 6.7 watts. That's a lot. In addition to the wasted power, it also heats up a circuit board. And keep in mind that you cannot hold your finger on a 1/2 watt resistor dissipating 1/2 watt. No doubt this requires a heat sink, another expenditure and some ventilation techniques, holes in the back of a cabinet or whatever. So that's the math on it. Good thing about it is that these are good regulators. They're quiet, but in certain cases they're just not good for high volume, low cost material where you're trying to get everything in a very, very small package. So let's take a look at an actual switcher here, and this is an example, is a block diagram of a boost mode switching regulator, and what that means is that the output voltage is going to be higher than the input voltage. So this is the main block of the regulator right here in orange, and this little wire coming in orange is the sense lead. So the regulator has to sense the output so it knows what to do. If, say, the output of this were to be 3.3 volts and it climbed to 5 volts, we could damage microcontrollers or other integrated circuits that would be serving, in general, as our load resistance here. So failure in a regulator can cause a lot of damage downstream. The extra parts here that we have to add from the standpoint of the circuit is an inductor, a fast diode. And the reason is because the storage time of this has to be low. When you change the voltage from a forward bias to a reverse bias in a diode, it takes time to pull that charge away from the junction to form a depletion region. And during that time, you have a relatively large current and a high voltage equals hot. So these are special diodes. I've shown, like this, a Schottky guy is a metal to N type. And there are other fast diodes too, but you got to watch the speed on those. This will eat 1N4000X regulators. We have an output catching capacitor here. We call it a filter. It basically takes the pulses coming out of this and stores them, and then that in turn is provides current for the load. And very important here is we have a fine, nice, low ESR capacitor on pin across the input of the regulators. This actually supplies a lot of the energy to the regulators, because when this turns on, there's a drop in VCC coming in on the circuit traces, and the ground is also going to bounce positive. So this capacitor actually provides energy into the switch mode regulator while it's in the process of charging our output capacitor. So let's take a look at the way this works. And this switch here is really MOSFET. I've shown an N channel here, and for high efficiencies the RDS(on) of this part has to be very low, and that just looks like a resistor that when the FET is turned on completely, it looks like I said, a physical resistor, and the loss would be equal to I squared times RDS(on). So the lower that resistor is, the better, and nowadays we're talking about tens of milliohms. So let's just pretend this is a transistor here, and we're going to close the switch for a minute, and when we do, we have current flowing into the inductor, down through the switch, back out to the source. The voltage drop, and what we're saying is we're charging the inductor, is plus to minus across the inductor. So when we charge an inductor, what that means is the magnetic field builds out. Now, this here point at this particular time is probably very close to ground, 0 volts. But we don't have to worry about the output capacitor discharging back into our switch because it can't go backward through a diode. Now the switch opens. Well, inductors don't like current to change. So if this generated a standard drop of plus minus in this polarity when the inductor was charging, when the magnetic field begins to collapse, it wants to keep the same direction of current flowing, so the output of the regulator changes polarities. Since the switch is open, that current discharge path now goes through the diode and charges the capacitor. So first we charge the inductor, then we discharge it, and that's all switch mode supplies do. Now the losses in here, as I spoke to, was that of the transistor, of course. We're going to pick up a loss in the diode, and also the little bit of loss in the inductor here, which would not only be the resistance of the windings, but also skin effect. That's where the effective resistance looks to be higher than it is because current only flows on the outside of a wire at high frequencies, not on the inside. Things like that. It also radiates a little bit, an antenna, and that can interfere with other sensitive components. Any radiation is considered a loss. If it doesn't If it is not part of the collapsing magnetic field, then it's considered a loss. So with this, what we can see is that we obviously want to have smallest parts possible, and a nice small inductor here with a high Q, and that Q is the reactance to resistance ratio of the inductor at the specified operating frequency. And what we find realistically is the efficiency of a switch mode regulator will climb to some sweet spot and then drop off. So as we increase the switching frequency, and that means that the inductor can be a smaller value, we're going to reach a point where we're going to have additional losses, a point of diminishing returns, and what we want to do then, or the designers that come up with this, would want to operate this very close to its maximum efficiency point. So let's see here, if we go lower, typically we need a larger inductor. And at all times, this is important, if we take a look at the charging time constant of an inductor, what we'd see would be something like this, and then we learn that it asymptotes out toward an I max. This is where we're operating, right in here. This needs to be a very, very straight line, because as soon as we start to curve this, means that the inductor is starting to saturate. That's bad. So these inductors are not air coil, but they're ferrous metal, and they can saturate. So if we're looking at the output of a waveform, say with a scope here, is what we would expect to see as a ripple component is a sawtooth with very, very straight edges, and some glitches and noise in there too. But so it's very important that the inductor does not saturate. So this is a boost mode supply, and the feedback would sense how long the switch is closed, how much current is charged in the inductor will determine the pulse of current feeding into this. So this is not capable of buck mode, to step down, but it will step up. Now one other thing here is, let's assume that we're, I don't know, 100% efficient, and our output voltage is 5 volts, and our output current is 0.5 amperes. The input voltage, we'll say, is 10 volts. And the input current under that circumstance would be 0.25 amperes. So this is going to give us 2.5 watts of input, and this is going to give us 2.5 watts of output. Now what's strange in a boost mode regulator is the input current is less than the output current. Now realistically, the input current under the voltage I've given you would be higher, because this is not 100% efficient. Now if we look at a buck mode switcher, we see kind of the same thing, except we're rearranged a little bit. This is our switch mode regulator here, and this is just more than a FET. It also has control transistors in it, and here's my sense line again coming back to tell this switch when to open or close. And in the case of the boost mode, the longer that switch is closed, the larger the field, and that's the way it controls the load, is by letting that inductor charge longer to get more energy out of it. And the same is true for this. So let's see how this works. We'll start with the switch being open. It's not too exciting. This capacitor again does the heavy lifting when it comes to supplying the buck mode regulator with current when it's in the switching mode. On pin, low ESR. So we just started this up, and what we can see is that our output voltage is very low, so the switch will close. When it closes, what we have is a current, and it cannot go through this diode because it would be reverse biased, goes through our inductor, charges our filter capacitor here, and also feeds the load. The drop across the inductor is plus to minus. So we're moving up toward feeding the load, but at some point our sense line is going to say, well, we're kind of getting on the verge of being too high. So the switch opens, current's flowing in this direction. The plus to minus that I've indicated here in red has to do with the magnetic field growing. When the switch opens, that magnetic field collapses, the voltage across the coil changes polarity, forcing more current into the capacitor and current into the load, and then the discharge path would be through the diode like this. So the time that the switch is closed and open, again, is determined by the load on this. Now, before going on further, I need to say this, and there's another topology called boost buck, but that's a combination of the two and fairly complicated. it can boost the voltage if the source is low and buck the voltage if the source is high, and that requires it to basically switch over between the two modes. Now suppose we did not have a load out here and this were to be continually switching back and forth. It is very possible that we could overcharge the capacitor. Now what I'm saying about that is that would be called a continuous mode switching power supply. If it's continuous mode, you'd always have a pulse, say at a switching frequency of 52 kilohertz. And it's possible that this voltage would exceed the output rating because the switch has to be closed a little bit during each cycle. Now you might say, that doesn't make sense. Well, it kind of does. In a continuous mode supply, you may have a minimum current rating, say 0.5 amperes, up to a maximum of, say, 2 amperes. What happens if we shut this off completely is that we would have pulses, well, like that. And these guys can enter the audio frequency. So you can have subharmonics which cause interference if it's a non-continuous mode regulator. So when you're dealing with power supplies, it's always good to look at them and see if you have a minimum load rating. And that'll tell you whether it's continuous mode or non-continuous mode. In some cases this doesn't happen, it's subharmonic stuff. In other cases it's very critical. So that would be a good example. And in some computer power supplies, by the way, if they're rated say at 400 watts and that would be a linear supply, you'd need 2 hands to pick it up, is some of the outputs have to have a load. You can't operate them as a bench supply per se. Now let's take one further step into switch mode power supplies, and this is very similar to that of a regulator, and it's similar enough that we can combine them at the same time. And what I'm going to do is take a look at a linear power supply here, and it's going to start out with a transformer, and then if we wanted to, I suppose we could run this into a bridge rectifier or whatever and end up with our DC output voltage. And when we look at this coming off 120 volts at 60 hertz, is what we know is that the period of that is 16.6 repeat milliseconds, and the half period of that is 8.3 repeat milliseconds. That means that the iron core in this has to store energy for at least 8.3 milliseconds. Now to put this in the picture here, this is a 20 watt monoblock audio amplifier. Everything you see from my hand up is the power supply. This is the power transformer. These silver guys here are the filter capacitors, and this here vacuum tube could be replaced by, let's see, 2 1N 4007 regulators, which cost 20 cents a piece. And this is half-weight, it's not even as good as a bridge. This whole thing could be replaced in switch mode by a part that's half the size of the transformer. So you can obviously see the advantage of that, and that power supply, by the way, is not regulated. So if we take a look at what we have, and the 8.3 milliseconds for an iron core transformer should be the key that's going to allow to understand this, is if we take raw 120, RAW, raw, not isolated. Here I've just shown a half-wave rectifier. This can be a full-wave bridge. We have a filter capacitor here to convert this into DC, and the example I'm using here, this output can range from 120 to 170 volts DC. We're going to be running a high voltage oscillator here, which through an opto-isolator probably is controlled by the output voltage. This is also feeding a transformer, only this transformer is a high frequency transformer. And if our switching rate is 100 kilohertz, that means it's turning current on and off to this transformer 100,000 times a second. That transformer only has to store energy for 5 microseconds. Hence, it can be a lot smaller. A lot smaller means that it's much more cost effective. Further, it can have multiple secondaries like a computer guy has. And the core in here would be ferrous, not iron, which is a mixture of kind of like iron and powder. Also note, and this is very important, that there are 2 grounds. Now the reason there are 2 grounds is suppose that your house wiring were reversed. This was ground and this was 120 high. If we had a common ground, that means your computer chassis would be 120 volts above ground. So this transformer here provides isolation, so we really don't care what happens on this side of the circuit with regard to grounds. Should be wired right, but if it isn't, not going to kill anybody. The opto-isolator is the guide that allows you to go from friendly voltages to hostile voltages. There needs to be some way of isolating it, and optos aren't the only way. They also have capacitive isolators also, which work in a similar manner. So that's an overview on switchers, and thank you for watching.